We know that the derivative for the natural log of x is equal to 1 over x, right? So we can use this idea, we can get the integral for 1 over x is equal to the natural log of x, right? So here is one thing. The integral of 1 of, instead of using x, we use another letter u, and the du, it should be, we take the derivative of a function which will recover 1 over u. So this one should be the natural log of u. But in order to guarantee the domain of the natural log is positive, so we add an absolute value sign, right? So that is one rule for the natural log function for in the integrations. So now let's look at some problems. Let's look at the first problem, 1 over x plus 2 dx. Okay. So it's not 1 over x, it's 1 over x plus 2, right? So far, we cannot use the rule directly. So at this stage, of course, after later you are familiar with the substitution, you can get the result directly. But at this stage, we still use the substitution. We introduce the letter, a new variable u is equal to 1 over x plus 2, so du equals dx. So this integral becomes 1 over u and du, right? So you can calculate it's equal to the natural log of u plus a constant, and the plugging back u is equal to x plus 2. So this is your result. Next example. This is the 1 over 2x plus 1 dx. Okay. So this problem, same idea, we let u equals 2x plus 1, so du is equal to the derivative of 2x plus 1 times dx, which is equal to 2 times dx, right? So here is, so we can calculate the dx, so this dx is equal to 1/2 du, right? Then we plug in here, it would be the integral of 1 over u times 1/2 du, right? So it's equal to 1/2 the integral of 1 over u du, right? So this is equal to 1/2 the natural log of the absolute value of u plus a constant c times 1/2, which is still a constant c. Then at last, you will see that it would be the 1/2 natural log absolute value 2x plus 1 plus a constant c. Okay. So be careful. So we always have students write this. The result would be the natural log of the absolute value of 2x plus 1 plus constant. They forgot this 1/2. Where the 1/2 from? 1/2 is from this differential, right? You will get this result. This is the 1/2. 1/2 is from here. Okay. Now let's look at this example. X over x squared plus 1 dx. We still let u be, in general, we always choose u to be the complicated part, right? So here is what would be the x squared plus 1. So du is equal to, we take the derivative of x squared plus 1, which would be 2x dx, right? So but we have no 2, right? We only have x and dx, right? So we can calculate x times dx equals 1/2 du. So your result would be, our new integral would be 1 over u and times 1/2 du. So we take the constant out, it would be 1 over u integral. Right? It would be 1/2 natural log absolute value of u plus constant c. So 1/2 natural log x squared plus 1 plus constant c. Next example, we have the integral secant squared over tangent x dx. So we do some observations and we notice that if we let u equals tangent x, then take the differential of u, it would be the derivative of tangent would be the secant square. So it's reasonable to choose u equals tangent x, then du is equal to the derivative of tangent x times dx, which is secant square, right? So we can write this one as the integral of 1 over tangent x, which is u, secant square times dx would be du. So you can have this one. This is the natural log absolute value of u plus constant. Then you plug in back, it would be the natural log tangent x plus constant c. Let's look at this example. The integral of 1 over x times the natural log of x dx. Okay? So which one we should, what is the u we should take? Let's think about, okay, if we take u to be the natural log, right, take the derivative, it would be 1 over x, which will recover, right? This here, this is 1 over x, right? This is 1 over x, right? This is 1 over x. So it's reasonable to let u to be natural log of x, so du equals 1 over x dx, right? So this is 1 over x dx, so it would be the integral of 1 over u and the du, right? So this is equal to natural log of absolute value u plus c, and this is the u is the natural log of x plus constant c. Integral of tangent x dx. Okay. If you look at this one, it only have a single one, right? Single function. So we can think about to change this one a little bit, right? Tangent x to be the sine over cosine x dx. Right. So if we take u equals cosine x, then take the derivative, it would be the negative sign. So we have the sine x dx, right? So this is the reason we choose u to be cosine x. So du is equal to negative sine x dx. Right? Negative sine x dx. So sine x dx is equal to negative du, right? So we can write this one as the integral 1 over u, right, times negative du, right? We put negative in front, it would be this one. So this one we know how to do, right? Absolute value u plus constant c, so it's equal to the negative absolute value of cosine x, the natural log, plus constant c. Okay, so now let's look at this example. X squared plus x plus 1 over x squared plus 1 dx. Okay. So if you choose the bottom one as our u, you take the derivative, you only have x, right? 2x dx, right? Then, but on the top there's x squared, so it's not it's not a good choice to choose x squared plus 1 as our u, okay, here in this problem directly, but we need to change a little bit. Let's do a long division. Especially on the top, the power, the degree on the top is greater than the degree on the bottom. This is rational function. If you have this case, you always do a long division first, right, to simplify our problem. X squared plus 0, x plus 1, right? So this is 1 x squared plus 0, x plus 1. So you do the subtraction, it would be x left. So it means x squared plus x plus 1 over x squared plus 1 is equal to 1 plus x over x squared plus 1, right? So we can rewrite this one as 1 plus x over x squared plus 1 dx. Okay, for this problem, you can separate into two integrals. One is the integral of 1 dx plus another one is the integral of x over x squared plus 1 dx, right? For the first one, it's very easy, right? Because you can use the result. You can use the antiderivative 1, which is x, right? Because you take the derivative of x equals 1. So you can get the first integral easily. What about the second one? So the second one, we need to use substitution method, right? So we let our u equals x squared plus 1. Okay, so du equals 2x dx. You can see we have the x times dx, right? So x times dx equals 1/2 du. Okay. Then we plug in. You will have the integral of 1. This is the first one, right? Plus this one would be the integral 1 over u times 1/2 du, right? So the integral of 1, which is x, right, plus a constant. Then this one is the 1/2, right? 1/2 is constant times the natural log of the absolute value of u plus another constant. So two constants add together would be a new constant. So this one would be x plus 1/2 natural log. We plug in back. Okay, so this is your answer. Let us look at a hard one. Okay, secant x. So the secant x is 1 over cosine. If you write as a 1 over cosine, it still doesn't helpful, right? So let's think about, maybe we can rewrite the secant x as we multiply a fraction which is 1, but this fraction is a very special fraction, which is the secant x plus tangent x over secant x plus tangent x dx. So this is actually 1, right? This is the 1. This is the 1. So why we choose this one? The reason is, if we let u equals secant x plus tangent x, then du equals the derivative of secant, which is the secant x times tangent x, plus the derivative of tangent, which is the secant square, then dx, right? What is this? This is actually the top, right? This one is actually this one. So you can see, you can rewrite this one as, let's write here, it's equal to the integral 1 over this denominator u, this part secant x times secant plus tangent dx, which is du. You can see it's very easy, right? It becomes very simple integration. It would be the natural log of the absolute value plus constancy. So what's that? This is the natural log, the absolute value, secant x plus tangent x plus a constancy. Take the absolute value.